Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to try and imagine something for a second. Imagine closing your eyes, settling in for a long winter nap, and just sleeping for almost an entire year.
I mean, that sounds pretty nice, honestly.
Oh, right. But then when you finally open your eyes, you aren't in your bed. You are nearly 6 billion miles away from home, drifting through the freezing pitch-black expanse of the outer solar system.
That is, well, that's the ultimate extreme wake-up call. You're out there in the Kuiper Belt, far beyond the familiar orbits of Neptune or Pluto.
Yeah.
In a region of space that is just profoundly dark and unimaginably cold.
And you aren't just drifting aimlessly, you have a job to do out there, which is the exact reality of NASA's New Horizons spacecraft right now.
Yep.
It recently awakened from its longest ever hibernation period. We are talking about a machine that's been out there for 2 decades, surviving against the harshest elements of deep space. And it is still managing to phone home and tell us what it sees in the dark.
It really is incredible.
So today, we're going to explore the mechanics of its survival, the secret work it does while sleeping, and the monumental legacy of its journey. Okay, let's unpack this.
So, to truly grasp the stakes of this awakening, we have to look at the timeline. New Horizons went into this deep sleep mode on August 7th.
Okay.
And it didn't wake up until June 23rd of the following year.
Wow.
Yeah, that is a 321-day hibernation. The mission team actively places the spacecraft into this resource-saving mode during these long cruise periods.
Because, out there, the sun is really just a particularly bright star in a black sky, right?
Exactly. Power is incredibly precious. Solar panels are entirely useless that far out.
Which means it has to carry its own power plant. So it relies on a radioisotope thermoelectric generator, or an RTG.
Right.
And for those unfamiliar with the mechanics of an RTG, it's essentially a battery fueled by a decaying lump of plutonium-238. As that radioactive material decays, it generates heat.
And then thermocouples basically convert that heat into electricity.
Right, but because of the nature of radioactive half-lives, that power source is constantly dwindling, so it produces less power today than it did yesterday.
Oh, absolutely, and much, much less than it did when it launched back in 2006.
Yeah.
That decaying power curve is really the central constraint of the entire mission. You have to conserve energy wherever you can, hence the 321-day sleep.
Right.
And you are managing this dwindling power supply across an incomprehensible distance. The spacecraft is currently about 5.9 billion miles from Earth.
That's hard to wrap your head around.
It's about 9.5 billion kilometers. So at that distance, we aren't just dealing with physical space, we are dealing with the tyranny of the speed of light.
Which fundamentally alters how you communicate with it.
Yes.
Like when the flight controllers at the Johns Hopkins Applied Physics Laboratory in Maryland were waiting to hear if it survived this long sleep, they couldn't just ping it and get an instant readout.
No, not at all. The communication delay is staggering. Radio waves travel at the speed of light.
Which is 186,000 miles per second.
Right. But even at that ultimate speed limit, those signals took exactly 8 hours and 52 minutes to cross that gap and hit NASA's Deep Space Network station near Madrid, Spain.
Man. So you sit at a console in Maryland, you initiate a command sequence, and your workday is essentially over before the spacecraft even hears you.
That's exactly it. It completely redefines the concept of remote control.
I like to think about it like having a conversation via extreme snail mail text message.
Yeah.
If you hit send on a simple question like, hello, are you awake? You have to wait a full workday and a night's sleep just to see the read receipt.
Yeah, that's a perfect way to look at it.
You send the message. 9 hours later, the spacecraft receives it. It immediately fires back a yes. Then you wait another 8 hours and 52 minutes for that yes to wash over the antennas in Spain.
Right.
So you're looking at a nearly 18-hour round trip just to exchange a single basic greeting.
It demands an extreme level of patience and foresight from the operations team. You just cannot micromanage a spacecraft when your control inputs have an 18-hour lag.
You really have to trust the systems you put in place.
You do. And that actually brings up a fascinating nuance about this hibernation phase. When we say New Horizons was sleeping for 321 days to save power, we do not mean the whole machine went dead.
Right. It wasn't just a lifeless metal brick floating through the void. It was actually keeping a massive secret from the emptiness around it. It was working the entire time.
Exactly. So during hibernation, the operators back on Earth send 0 commands.
Right.
They are maneuvering it, they aren't actively running diagnostic tests, and they aren't retrieving any data. But Alice Bowman, who is the mission operations manager at the APL, she confirmed that the spacecraft was autonomously sending back a weekly status beacon through that deep space network.
Like a green beacon, right?
Yes, a simple ultra-low power pulse that basically whispers into the dark, I am alive, systems are nominal, the temperature is stable.
Just a little heartbeat.
Exactly. And Bowman noted that every single status report through the entire 321-day hibernation period was green. Every single week, like clockwork.
That is wild. And beyond just maintaining its own heartbeat, the scientific instruments on board never stop either, do they?
No, they don't. The hard drives are actively filling up because several key sensors run around the clock, just tasting the vacuum of space.
Wow.
The instruments they keep running are vital for understanding the extreme edge of our solar system. For instance, there are the heliospheric plasma sensors.
And the solar wind at Pluto instrument, which they often call SWAP,
Right.
along with the Pluto Energetic Particle Spectrometer science investigation.
So these instruments are out there measuring charged particles in magnetic fields.
They're trying to understand the boundary layer where the sun's magnetic bubble, the heliosphere, starts to give way to the interstellar medium.
So the solar wind is pushing out and the rest of the galaxy is pushing back.
Exactly. And New Horizons is flying right through that collision zone, constantly sipping data from the environment. Okay, but there is one instrument on that active list that I find absolutely brilliant. Because alongside all these heavy-sounding plasma sensors and spectrometers, there is the Venetia Burney Student Dust Counter.
Oh, yes. The dust counter.
It's literally a space dust detector designed by college students. On a multi-billion-dollar mission to the edge of the solar system, we basically bolted a highly advanced dash cam to the windshield, or like a cosmic bug zapper.
Yeah.
But why are we so concerned with tiny specks of dust out in the dark when the whole goal was exploring massive planets? It's like leaving your dash cam running while your car is parked in an unfamiliar neighborhood just to see what debris hits the glass.
What's fascinating here is that in the Kuiper Belt, dust is not just dirt. It is the historical record of the solar system's formation.
Oh, wow. Okay.
The Kuiper Belt is this massive ring of icy bodies and primordial debris left over from the birth of our planetary neighborhood. So when these ancient objects occasionally bump into each other or they get struck by micrometeorites, they generate dust.
But how do you even count dust out there? I mean, we are talking about a piano-sized probe flying at 36,000 miles per hour in absolute darkness.
Right.
How does it detect a particle that is smaller than a grain of sand?
The mechanism is actually remarkably elegant. The student dust counter uses these specially polarized plastic films. Polyvinylidene fluoride, to be exact.
Okay.
So think of it like a highly advanced electrified plastic wrap. When a microscopic dust grain hits that film at 36,000 miles per hour, it vaporizes on impact.
Just vaporizes.
Yep. That tiny, violent collision physically punches the material and generates a minute electrical signal. The instrument registers the electrical spike as a single hit.
So by leaving that specific instrument running 24/7 during hibernation, we're getting an uninterrupted baseline measurement of exactly how much debris exists out there. We're basically driving through a completely uncharted forest and counting the bugs on the windshield to figure out how dense the trees are.
Yeah, and it tells us about the frequency of collisions happening millions of miles away from the spacecraft itself. Because the operators aren't pulling data down during those 321 days, New Horizons has been quietly storing all of these electrical spikes, all of these plasma measurements. It has just been acting as a silent observer.
Which creates a massive bottleneck now that the alarm clock has gone off, right?
Definitely.
I mean, it's June 23rd, the spacecraft is awake, and those onboard hard drives are absolutely stuffed with nearly a year's worth of data.
Yep.
And you have a spacecraft 6 billion miles away operating on a transmitter that outputs roughly 15 watts of power.
Yeah, that's really nothing.
It's less power than the LED light bulb sitting on your desk. You cannot just download gigabytes of data over a connection that faint. So how do they prioritize what gets sent back through that tiny 15-watt straw?
Well, you've hit on the exact logistical nightmare the downlink team faces. It requires a carefully orchestrated sequence. They do not just ask for the science data immediately.
Yep.
First, they exclusively downlink the critical health and safety telemetry. They need to verify the absolute status of every single subsystem, check the thermal readouts, and measure the exact power output of the RTG.
Basically making sure nothing fundamentally degraded during the long winter.
Exactly. Because if a heater failed or, a memory bank corrupted, you need to know that before you start demanding heavy data transfers that strain the system.
That makes sense.
Once health and safety are fully confirmed, then they begin the slow, methodical process of downlinking the stored science data from the dust counter and those plasma sensors.
And they don't waste any time getting back to active, targeted science either.
No, they don't.
Roughly 3 weeks after waking up, they bring another major instrument online, which is the ALICE ultraviolet spectrograph. Now, the ALICE instrument is tasked with looking at the distribution of hydrogen gas in the outer heliosphere.
Right.
But wait, how does a camera looking at ultraviolet light tell us anything about hydrogen gas floating in the pitch black?
It acts sort of like a cosmic barcode scanner. Different chemical elements absorb and emit specific wavelengths or colors of light. And hydrogen interacts very specifically with ultraviolet light. So even in the darkness of the Kuiper Belt, there is ambient starlight.
Right, from distant stars.
Exactly. And when that starlight passes through a cloud of hydrogen gas, the hydrogen atoms absorb very specific ultraviolet wavelengths, which leaves dark lines in the light spectrum.
Oh, I see.
The ALICE spectrograph splits the incoming light, kind of like a prism, and looks for those missing dark lines. The thickness and depth of those lines tell the scientists exactly how much hydrogen is out there and how it's distributed.
That is so clever. And while Alice is scanning for those barcodes, the solar wind at Pluto, the particle spectrometer, and our favorite student-designed bug zapper just keep right on taking their constant background measurements.
Yep. All while the ground team is running a series of spacecraft and instrument checkouts to ensure everything remains calibrated. Operating a spacecraft that has been exposed to the radiation and deep freeze of space for nearly 2 decades requires continuous evolution.
Yeah, I'd imagine.
The team on the ground is completing upgrades to the ground system software to streamline operations, and they're testing those upgrades throughout the entire year.
But the most critical adaptation isn't happening on the computers in Maryland. It is happening on the spacecraft itself, right?
That's right.
New Horizons is currently operating on updated autonomy logic. Now, autonomy logic sounds incredibly sophisticated, but let's be blunt about what we are discussing here for a second.
Okay.
We are talking about letting a flight computer built with early 2000s processing power make its own life or death decisions. We are taking an aging, degrading machine 6 billion miles away, flying blindly through an icy debris field, and handing over the keys.
Yeah, that's one way to put it.
Isn't there a massive mission-ending risk in letting a 20-year-old computer manage its own operational faults without a human verifying its math?
It sounds incredibly risky when you frame it as handing over the keys to an antique computer, I'll give you that. But the physical realities of the outer solar system dictate that autonomy is not a luxury. It is an absolute necessity for survival.
Just because of that 18-hour communication loop we talked about earlier.
Yes. Think about the cascading effects of a system failure. If New Horizons detects a sudden drop in voltage from the decaying RTG, or a fault in a critical navigation sensor, it cannot afford to send an error message to Earth and wait 18 hours for the engineering team to diagnose it.
And then send a command back.
Exactly. In 18 hours, a minor power fault could cause the spacecraft's internal temperature to drop below critical thresholds. The fuel lines could freeze, the batteries could crack.
It would just be a dead frozen brick by the time our help arrived.
Exactly. So the autonomy logic is essentially a complex set of fault protection algorithms designed specifically for operations farther from the sun. The spacecraft naturally has less power now, and the radio signal travel time naturally increases every single day it pushes further outward.
So the onboard computer has to know how to save itself.
It does. If it senses danger, it is programmed to automatically shut down non-essential scientific instruments, forcefully route all available power to the internal heaters to keep the fuel lines liquid, and automatically point its main antenna directly at Earth to await rescue commands.
Okay, so we aren't giving it freedom to be reckless. We are giving it the reflexes it needs to survive the deep freeze when we physically cannot be there to hold its hand.
That's a great way to put it.
And handing the keys to that 20-year-old hardware makes a lot more sense when you look at its resume. To really appreciate why this machine deserves that kind of trust, you have to look at the consequences of what it has already achieved.
Absolutely.
It didn't just survive to reach the Kuiper Belt, it literally rewrote the textbooks on planetary science on its way there.
The timeline of this mission is just staggering. I mean, it launched in January 2006, and it launched fast.
Very fast.
It held the record for the fastest spacecraft ever to leave Earth orbit, departing at over 36,000 miles per hour.
And even at that speed, they still needed a boost.
They did.
By February of 2007, which is just over a year later, it intercepted Jupiter. But it wasn't just there to take photos of the gas giant and its moons, though it did capture some stunning atmospheric data. It was there to steal momentum.
Yeah, a classic gravity assist.
Exactly. It flew deep into Jupiter's gravitational well, basically using the planet's immense mass like a slingshot. By perfectly timing its trajectory, New Horizons siphoned off a microscopic fraction of Jupiter's orbital energy around the sun and boosted its own speed by another 9,000 miles per hour.
That single gravity assist was just a masterful piece of orbital mechanics. It shaved roughly 3 years off the total transit time to the outer solar system.
Which perfectly set the stage for the main event in July 2015, the historic first exploration of the Pluto system.
Yeah, that was huge.
Up until the moment New Horizons arrived, Pluto had just been a fuzzy handful of pixels in our most powerful telescopes. Scientists were debating whether it would just be a dead, cratered ball of ice. But instead, New Horizons flew past and revealed this highly dynamic, complex world with nitrogen ice glaciers, towering mountains made of water ice, and a massive, bright, heart-shaped feature dominating its surface.
It proved that dwarf planets in the distant solar system could still be geologically active. But because the navigation team had aimed the trajectory so perfectly through the Pluto system, the spacecraft actually retained enough fuel and momentum to push even deeper into the Kuiper Belt.
Which led directly to January 2019, when New Horizons achieved the first ever close-up exploration of a classic Kuiper Belt object, a small, icy body they named Arrokoth.
Yes, Arrokoth.
When those first images came back, it looked like a giant reddish snowman floating in the void. 2 distinct spheres joined at a narrow neck.
And that snowman shape was the crucial aha moment for astrophysicists, because for decades there had been 2 competing theories about how planets formed in the early solar system.
Right.
One theory suggested violent high-speed collisions that shattered rocks until they eventually mashed together. The other theory suggested a process called gentle accretion, where primordial objects orbiting in a cloud slowly drifted together, gently kissed, and stuck.
And because Arrokoth's 2 lobes were perfectly preserved and hadn't shattered each other into fragments, it proved the gentle accretion theory.
Exactly.
That little red snowman, billions of miles away, fundamentally proved how the Earth itself originally began to form out of the cosmic dust.
If we connect this to the bigger picture, since that flyby, it has just kept going. It's conducting unique studies of the sun's outer heliosphere and observing dozens of additional Kuiper Belt objects from a vantage point that no other human-made spacecraft currently possesses.
You know, it's wild to think about the human scale of this timeline.
Oh, yeah.
I mean, New Horizons launched in January 2006. Someone born on the exact day this spacecraft punched through Earth's atmosphere is now entering their 20s.
That's crazy to think about.
They might be in college or starting a career. They have lived an entire phase of a human life. And for that entire time, every day they went to school, every birthday they celebrated, this little piano-sized probe has been hurtling outward through the dark at tens of thousands of miles per hour, never stopping.
It represents a literal multi-generational baton pass. The scientists and engineers at the Applied Physics Lab who designed the initial concepts for New Horizons back in the 1990s and early 2000s knew unequivocally that they were building a machine whose final data sets would likely be analyzed by students who hadn't even been born yet.
Wow.
It's a profound act of scientific optimism. You build the hardware, you aim it into the dark, and you trust that the next generation will be there at the receiver to catch the signal.
We build these machines to outlast our own careers. We build them to go where human biology absolutely prevents us from going and to keep our eyes open in the dark for as long as physics allows.
And that actually raises a compelling final thought regarding the ultimate fate of this mission. New Horizons survived this 321-day sleep. The weekly beacons were green.
Yeah.
The instruments are humming. The autonomy logic is successfully managing the thermal constraints. But eventually, the laws of physics will win.
Yeah, that power source.
Right. The plutonium-238 inside that RTG will decay to a point where the spacecraft can no longer generate enough wattage to keep its internal heaters running, let alone power a 15-watt transmitter to send data back to Madrid.
It will truly, permanently go to sleep.
Yes. Consider what happens after that moment. Long after the ALICE spectrograph finally shuts down, long after the onboard computer stops processing its fault protection algorithms, and long after those faint radio signals fade entirely from the deep space network, the spacecraft itself will still be out there.
This drifting.
It has achieved escape velocity from our sun's gravitational pull. It won't stop moving. It will drift endlessly out of the heliosphere and into the interstellar void. A silent frozen capsule. A permanent physical monument to human curiosity, continuing its journey through the Milky Way long after we stop listening.
Just a permanent artifact of us, carrying a dust counter built by college students coasting forever between the stars. That is a brilliant thought to end on. To everyone listening, thank you for joining us as we trace the path of this extraordinary machine to the farthest reaches of our solar neighborhood. Next time you settle in for a nap, just be glad you get to wake up in a warm bed and not 6 billion miles away in the freezing dark. Stay curious.